Welcome to this introduction to understanding metadata schemas by SDSC, GoFair US and partners. This video is hosted by the NIH Office of Data Science and Emerging Technologies and GoFair US. So, what do we need to know about metadata schemas? In general, there are already robust metadata schemas published by authoritative bodies like schema.org, specifically designed to maximize findability. It saves time and guarantees that our data is instantly compatible with global discovery tools and community repositories. The NIAD Minimal Metadata Schema is strategically built upon schema.org. By leaning on this global standard, the schema remains minimal, focusing only on the essential elements required for discovery. This approach ensures optimal interoperability, making it easier for NIAD-funded data to be indexed and found by major search engines and research registries alike. Beyond simple discovery lies the need to know more about data lineage and used protocols. To support deeper reuse, we often must extend metadata standards to develop community-specific schemas for provenance. This way, we provide the granular context required for researchers in a specific field to fully understand and replicate scientific results. Developing community-specific schemas requires a consensus-based approach. Make sure to build a process where your peers can actively shape the final metadata structure. Because the entire community must apply these standards to achieve maximum interoperability, active participation and agreement are just as important as the technical specifications themselves. This sense of collective ownership makes the difference and ensures that the schema meets the practical needs of the researchers using it. Reuse and extend first, but if you must create new metadata elements, don't leave them orphaned. Make sure to map your custom elements to existing standards using machine actionable crosswalks. These mappings are the translation layers that allow your specialized metadata to remain compatible with global discovery tools and interoperable ecosystems. Now, let's get practical. Here is a reusable template in the form of a Google Sheet designed to guide you through the schema creation process. We are going to break down every section of this template, exploring how each part works and why it matters. By understanding the functionality behind these components, you'll be able to build a schema that is not only robust, but fully compliant with global standards. Starting with column A, we find the structural backbone of our schema. This column helps you organize your metadata into distinct sections that cover different topical aspects of the data. Whether it's administrative info, scientific context, or legal constraints, these sections allow you to group related elements together, organizing the metadata into a logical structure. Column B is dedicated to the metadata element, commonly known as the metadata field. These elements can be presented either as concise field names or formulated as questions to prompt the user. Regardless of the way they are presented, they must be carefully crafted for comprehensibility. To improve data quality, we recommend including guide text, instructions, and field definitions. While these extra columns are omitted here to save space, adding them to your local editor will help providers create more accurate and consistent metadata instances. Every metadata field requires a specific answer type. In column D, we define the data type expected. For many elements, we still require standard formats like pure text, dates, or numerical values to capture specific attributes of the data. Alongside these, we use Unified Resource Identifiers, or URIs, for elements that require a persistent global reference. It is important to distinguish between the two ways we use these identifiers. First, we use URIs to link to other digital objects, creating a direct connection to external resources like a specific instrument or a related publication. Second, we use URIs to select terms from published controlled lists or vocabularies on the web. These answers represent the object in a metadata standard. So they are the values we ask for to describe a specific aspect of data. When we select controlled list as our answer type in column D, we must be specific about our source. In column E, we identify exactly which controlled list is required for that field. We provide the URI for that vocabulary where the terms we want to use are defined in a dedicated tab of this sheet. Column F defines the level of requirement for each field. Is it mandatory or optional? This categorization is vital for ensuring metadata completeness. By clearly marking required fields, we guide the user to provide the essential core metadata needed, while still offering the flexibility to include optional community-specific details that provide richer context. Column G specifies the cardinality, setting the rules for how many values a field can maximally contain. For optional fields, the cardinality must be interpreted as 0 to 1 or 0 to many. This tells the user that while the field can be left blank, if it is answered, we expect either a single value or multiple entries. For mandatory fields, the cardinality is 1 to 1 or 1 to many. This ensures that at least one answer is provided, but allows the flexibility for more than one when necessary. For example, when a dataset has multiple authors or several relevant keywords. We now come to column C, perhaps the most challenging but critical specification in the template. To make our schema truly interoperable and understandable by machines, the metadata field name needs to be complemented by a URI of the object property. Think of these as the predicates, the linking component in our metadata sentence that defines the relationship between the data and the attribute. Hence here the additional predicate label in both fields. These predicates must be borrowed from the object properties of existing ontologies. We should search semantic artifact catalogs to find properties that are already designed for datasets. Only if an exhaustive search yields no results should we consider the high effort task of creating new object properties in a new ontology. To bring it all together, let's review the metadata sentence structure as mapped to this sheet. While the subject isn't explicitly shown in a column, it is always the data or digital object itself. The predicate, the formal relationship, is defined by the metadata predicate field name and the chosen predicate URI in column B and C. Finally, the object specifications are captured in column D through G with its specific constraints, formats, and requirements. By filling out this template, you have established the semantic foundation for your schema. Find here exemplar metadata field specifications. 1. Identifiers which require URIs as the value type. 2. Names or titles which require free text input. And 3. Content-related metadata, for example, measurement techniques, which require terms selected from a prescribed controlled vocabulary, such as the NCIT terminology. This is the blueprint you need to finally implement a functional metadata template in any environment.